Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. Last time we were going through the design of CPU. We said that our central processing unit or a processor would primarily contain two subsystems, the data path and the control. The data path is dictated by the instruction sets, and that is processor dependent. In our last lecture, we were going through the Falcon A processor. We knew in our earlier lectures the instruction set and the behavioral RTL description of Falcon A. And we went on to our design step, which defines the RTL description in structural form. So the structural RTL. The structural RTL gives us more information on how the implementation of different instructions would take place. It has to be synchronized, and as a result, we define different activities in synchronism with a timing generator. So from a master clock, different timing steps are available. In our example of a unibus implementation, our timing generator has got 8 steps. So for all instructions, we had first 3 steps for fetching a particular instruction from the memory, and then execution has a variable number of steps, which could vary from 1 timing step up to 5 timing steps, altogether the maximum being 8. And at the end of each sequence, the timing generator is initialized back to 0. So every instruction starts from T0 and ends at T4, T5 or up to T7. We were going through the execution of different instructions for our Falcon A processor. We discussed the first functional group in the form of arithmetic and logical instructions with some examples, then load and store instruction, and then we went on to our branch instruction. Last time we ended up with our discussion on conditional jumps, and we said that in the case of conditional jumps, the variety in Falcon is more as compared to what is available in our simple RISC processor, RISC computer SRC. And we have a possibility of usually a near jump with a limitation of the constant. You might realize in this case altogether we have 16 bits in the instruction set and a maximum of 8 bits to define the constant, which would give us an effective address to which one needs to jump with reference to the present contents of the PC. We'll go on today and see rest of the instructions for Falcon A and define the structural behavior for using the RTL notation. So we'll go first for the unconditional jump, and then the remaining instructions would be discussed one by one. Let us look at the slides to illustrate these ideas. The slide is a recall from previous lecture and indicates the unconditional jump with an opcode 20. Opcode followed by a 3-bit description for register RA, and then followed by a constant C2, which is an 8-bit constant. As in the case of unconditional jump, we could define the jump in the form jump RA plus constant, or a variable, or an address, or a label. In the case of a constant, variable, address, or label minus PC that should range from minus 128 to 127, and that comes from the restriction on 8-bit constant C2. Now if the jump with R0 plus A is used, it means jump to RA when the register placeholder value is 0. Now if we have jump minus R2, that is not allowed by the assembler. The target address should always be even because we have each instruction with 2 bytes. So the addressing modes available for this unconditional jump is either we have a direct or indirect or PC relative or register relative. In the case of direct jump, the constant C2 straight away defines the address to which we need to jump. In indirect, C2 would indicate the indirect location in memory from where we find out the contents, and we could have a far jump in this case. For PC relative, if the contents of the register RA are 0, then we have a near jump and it is PC relative, whereas if contents of register RA are not 0, we have a far jump and the contents of RA are updated, added with the constant C2 with appropriate sign extension. The RTL structural description for jump, unconditional jump, is indicated in the following slide. In the unconditional jump, we have jump within square brackets RA plus C2 as a constant. In the first 3 steps, we have instruction fetch. In timing step T3, depending upon the contents of RA, so within brackets RA equal to 0 would either be true or false. If it is true, then we take the contents of a program counter PC and place it in temporary register A. And if RA is not 0, then what we do, we take contents of RA and place it to A. Now the comma indicates that these two are concurrent, and in fact only one of these two conditions would be met. If we have the contents in the register as 0, it would indicate a PC relative jump. And in the other case, when the contents of RA are not 0, this would be an example of a register relative jump. In timing step T4, we add the constant C2 with appropriate sign extension to the contents of register A using the ALSU unit, and as a result, at the output, we would have in buffer register C the effective address to which we need to jump. In T5, we take the contents of C and load it to the program counter PC, which would just give us the position to which we need to jump through execution of this particular instruction. The next group of instructions is the shift instructions, shift and rotate also. First example is shift right. The syntax would be shift right, RA, RB, and constant C. Remember that this constant C1 is the count field. So the 5-bit constant that is obtained from the lowest 5 bits available in the instruction register IR. Again, the first three steps indicate instruction fetch. In T3, we load an arbitrary register N, 5-bit register, from the lowermost 5 bits of the instruction register IR, and then in T4, depending on the value of N, capital N, which indicates the decimal value of the register small n. Small n indicates the register and capital N indicates the decimal value available in this register. So what we do, we take the contents of register RB and shift it right by capital N bits, which indicates how many shifts are to be performed. So as a result, we need to feed on the leftmost bits zeros, and that is indicated, 0 is replicated capital N times, and this is concatenated with the shifted bits, which are actually 16 minus capital N. So as an example, if the number of shifts were 2, we will shift by 2 positions and we will have 14 original bits. 2 bits would be lost, and on the left side we feed 2 zeros into that particular register. And after concatenation, as a result, we will have in buffer register C the original 14 bits shifted by 2 positions, and on leftmost 2 zeros. After this operation in T4, in the next timing step T5, we take the contents from C and through the internal bus feed it to the register RA, which is the destination register. Other instructions that would have similar tables are shift left and arithmetic shift right. We considered the structural RTL description for the shift right instruction. Arithmetic shift right is similar except for one difference, and the difference is that as the data is shifted right on the left side, instead of just pumping in zeros, we need to duplicate or place the sign bit available in the original data. So as an example, if it is a negative number, it's a 16-bit negative number, and let us say we shift it by 1, then the original data in bit position 15, C15 for example, when we say 0 to 15, the most significant bit would be 1 because it's a negative number. So as we shift it to our right, then the incoming data would not be 0, it would be 1 because it's a negative number. So you could represent it just in the form of RTL notation as a concatenation of the shifted data and copying the sign bit into the leftmost bits which are shifted. If it is shifted by 1, then we just extend and place the sign bit into the leftmost position. And if there are 2, then 2 leftmost positions would be just duplicated by the sign bit. For negative, it would be 1. For positive, it would be 0. Now, let us move on and see some other instructions in Falcon like move, call, and return. These instructions were not available in our SRC processor. And we quickly go through the structural RTL implementation of the remaining instructions for our Falcon A. The table shows structural RTL description for move instruction. Move RA/RB means that the data available in RB should be moved and placed in the destination register RA. RB gives the source and RA gives the destination register. So in the table, first three timing steps as usual are instruction fetch. T3 takes the data from register indicated by placeholder RB and we put it through the ALSU unit to buffer register C. In timing step T4, the buffer register C transfers its data to register RA through the internal unibus. There is move immediate instruction indicated in the next slide. And now we have destination register RA and a constant C2 is to be moved to destination register RA. T0 to T2 correspond to instruction fetch. Timing step T3 takes C2 constant and places it into buffer register C. Note that C2 is an 8-bit constant and register C is a 16-bit register. So we need to concatenate the remaining leftmost 8 bits with the sign bit. So therefore the sign bit is C2 within angle brackets 7, which indicates the most significant bit, which would be 1 if the number is negative and 0 if it is positive. So depending upon the sign bit, the remaining 8 bits are just replicated with this sign bit to make a 16-bit constant, and it is placed in buffer register C. And in timing step T4, contents of C are taken to the destination register RA. A very simple implementation for move immediate. In the case of our Falcon A, we have in and out instructions, and we assume that, which we did not explicitly indicate in our implementation, after fetching the in instruction in this particular case, in the first three steps, in step T3, we take IO within square bracket C2 says that go to the IO address indicated by the constant C2, which in this case would be a positive constant since it indicates an address, and from there data would be fetched, placed into C through the bus and through ALSU unit. In T4, we take from buffer register C and place this data into destination register RA. The out instruction would just be the opposite. First, we take the data from the source register RA and place it to an output port indicated by C2 constant. So it's just the opposite of the in instruction. The next table shows an example of a call instruction. In a call instruction, we need to give control in a program to a procedure or subroutine to another address which is specified. The syntax is call RA, RB. As usual, the first three steps would fetch the call instruction. In step T3, we store the present contents of PC into buffer register C, and then in T4 from C into register RA. So as a result, register RA would contain the original contents of PC, and this would be a pointer to come back after executing a subroutine, and it would be used later on by a return instruction. In step T5, we take the contents of RB, which would indicate actually to the point where we want to go to or give the control of the program to. So in T6, the contents of C are placed in PC. So as a result, the program counter would point to a position in the memory from where the execution needs to be started. So call is an instruction which just gives a control to an address given in register RB, and RA would just have the data regarding the original contents of PC. In the last slide, we have return RA. After fetching the return instruction in the first three steps in T3, we just take the data available in register RA to the buffer register C through the internal bus and through ALSU, and in step T4, these contents of the buffer register are placed to PC. So only two timing steps are required for execution of the return instruction. By now we have a fairly good idea of how to write RTL description of instructional form for different instructions. We have done that for two examples, SRC and Falcon A. So from the behavioral description, we went on to the structural description. We have assumed one thing till now. That means the activity on the bus or data in and out from different registers is synchronized, and we have appropriate control signals available to us. Now we will go into and look what are different control signals required and at what point of time, that means in which particular timing step do we need to generate the control signals. So now we will discuss what are different control signals, how these are available in different timing steps. Then we will also see the interface with the external devices, memory, IO devices, and other peripherals if so required. Then later on we'll see that two important registers which we have as an interface, the memory address registers and the memory buffer registers. What would be the circuitry around this and how do we implement it as a two-port register? So we will look into the implementation aspect of MAR and MBR. Finally, we will see that how different registers would be interconnected. So as a result, we need to go into a little bit of logic implementation, and we will assume that you have already previously done your logic course in a nice way and you have a pretty good idea about the conventional devices, gates, and the logic circuits. So first of all, with the help of one instruction, we will go into defining and looking into different control signals. We would have two examples. One is for Falcon, one is for SRC. I will start with the example of the Falcon processor and point out the differences as and when required regarding the SRC processor. Let us go to the slide for elaborating the control signals required in different timing steps. This slide is just a recall and just indicates the Unibus data path implementation for Falcon A. I've just shown this for reference, and the rest of control signals would refer to the registers available in this diagram, and the corresponding reference would be made in the following slides. Now this slide shows the control signals required for the fetch operation. As you know that fetch operation is implemented in 3 timing steps, and the table just shows the structural RTL implementation in the second column. In the third column, we have indicated the corresponding control signals. Let me explain this in more detail, how we can list the control signals. In timing step T0, the internal unibus is active and the contents of PC through the bus are placed in the address register MAR, and at the same time we increment the contents of PC by 2 and place it in the buffer register C. I hope you remember from the previous lecture that for any particular register we need to enable the load signal. Unless we have a load signal for a particular register, we cannot write into that particular register. In this particular case, for timing step T0, we need to write into the address register MAR from the bus. So therefore, we need to activate its control signal. So LMAR is the control signal for the address register. Now, PC has to provide the data to the bus, and it cannot do that unless its tri-state buffer is activated. So to activate and to enable the program counter to provide its data to the bus, we need the out control signal, which is named as PC out. Then the contents of PC are also available to the ALSU unit, and we have increment 2 as a function of the control unit. The ALSU is just a combinational circuit, and when we activate the PC, the contents over the second input of ALSU are available, and it is incremented by 2 and data is available in C. So we cannot write into C unless the control signal is available. So LC represents the control signal which would activate buffer C to get the data from the output of ALSU unit. Note here that increment 2 is one of the functions of ALSU, and at the same time it is also a control signal which needs to be provided. So it's very important you understand the whole idea of which particular control signals would be required to be activated in a particular step. So in T0, PC out is enabled. PC provides data to the internal bus by activating the control signal PC out. The data from bus is read into address register MAR by enabling or activating its load signal LMAR. PC through the ALSU function increment 2 that provides output to the buffer C, and we need to enable this buffer by providing the control signal LC. The control signal increment 2 also needs to be provided in order to implement the function of ALSU unit. In the next timing step T1, we need to read data from the memory indicated by address register MAR and bring this data from memory to the buffer register MBR. Since the internal bus is free, simultaneously, concurrently, we place the contents available in buffer register C into the program counter PC. In order to enable address register MAR to provide the output, we need to activate its tri-state buffer through a signal, through a control signal MAR out. So MAR out would provide MAR to give a data to an external bus for the memory read cycle. We also need to have a memory read control signal which is named as mRead in this case. This would be required for fetching data from the external memory as well. In order to enable buffer register C to provide its data to the bus, we need C out signal. In order to enable program counter to read in from C, we need to enable its load signal, and that is named as LPC. Now for the buffer register MBR to read in from the data which is coming from the memory, we need to enable load MBR, which is a load control signal for buffer register MBR. So in this particular timing step, we need to have 5 control signals. For PC, we just have LPC, enable the PC to read in from the bus, C out to enable buffer register to feed its data onto the bus, MAR out to enable the address register to give its data at its output, and mRead for enabling the memory to be read, and LMBR to enable buffer register to accept data which would come from the memory. In the next timing step T2, the data available in the buffer register MBR is to be read into the instruction register, and therefore the control signals would be MBR out to enable MBR memory buffer register to enable its data to be placed onto the internal bus now, and from the internal bus the data to be fed into IR. The load signal for instruction register is enabled by providing LIR. So these 3 steps from T0 to T2 constitute the fetch cycle, and it is important that in each timing step the appropriate signals are activated, and those signals, those control signals which are not required would have a value 0 and would be deactivated. It's important that we realize what happens during the instruction fetch. Previously we had RTL description, and now along with RTL description we have defined additionally the control signals which are required in each timing step. And please note that in each timing step all these control signals appear simultaneously. So the order in which we write these control signals is immaterial. So as an example, we could write load signal first, or control signal, or out signal. It would not make any difference as soon as all these control signals happen to be in that particular timing step. Now from one timing step to another timing step, the different control signals are disjoint. So we would say that when in T0 some signals are active, in the next timing step T1 another set of control signals would be activated. For those signals which are not mentioned in the table, those would be assumed to be as 0, that means deactivated. Now the function or the control signal increment 2 is a function of ALSU, and also it is a control signal. So when this control signal increment 2 is available, then ALSU would perform an increment 2, which would mean that the contents of PC are to be incremented by 2. But actually the PC would be added to, and through the buffer register C, then the data would be just pumped into PC. Now also note that since it is a Falcon processor, the instruction is 2 bytes long or 16-bit long, and therefore we have increment 2 instruction. Now in the set of SRC, you will notice that the fetch cycle is exactly similar, and we have the same control signals, except for the difference that instead of increment 2, we will have increment 4, indicating that the length of instruction is 4 bytes. So therefore the addresses in the memory need to be updated by 4 bytes. After having a look on the fetch cycle or the fetch control signals required during the fetch cycle, let us take other examples and see what other control signals would be required during the execute cycle, and that would depend on different instructions. So as pointed out earlier, the fetch part of instruction would be common to all the instructions, so it would not be repeated. The control signals would not be mentioned again and again, and as we discussed in the case of RTL description or structural RTL description, we will just take into account what additional or what different control signals would be required for different instructions. So we just see that from instruction to instruction, we will define additional control signals for the execution part of that instruction. Another important thing you should notice at this point of time, that the CPU has an interface with external memory and or the I/O, depending upon whether it is a memory mapped I/O or a non-memory mapped I/O. And some control signals would be required and would be generated by the processor and would be used by the memory or I/O to read or write data to or from the I/O devices or from the memory. We also have assumed one thing which was clarified in one of the earlier lectures also, that the read and write from the memory is fast enough. So in a given point of time, which in this particular case could be, for example, T2, the data T1 or T2, the data should become available within that timing interval to the CPU. If the memory is slow and it does not happen, we need to introduce the concept of handshaking. To simplify, we could say that we have to introduce some wait states, some idle states, and prepare our buffer till the data is available. These details we could discuss later on with reference to some particular examples, but for the sake of simplification, we can assume at this point that memory is fast enough, and in the fetch cycle, a particular data becomes available from the memory to the processor in the buffer register MBR. Let us now look into some examples for the execute cycle for different functional groups of instructions. The slide just symbolically shows what you already know. Let us say Falcon is available in the form of a chip, and we have external interface in the form of 16-bit address bus, 16-bit data bus, and some control signals available on the control bus. The control bus could include signals like mRead, memory write, IO read, IO write. If you just see a similar figure for SRC, then the width of address, data bus, and control bus would be different, and the control signals, which in this case include IO read write, in that case it would be only memory read write because IO would be memory mapped. Before we go on to the actual instructions to see into the execution, it is worthwhile to have a very simple example. And for this example problem, we would like to know what will be the logic levels on the external Falcon address bus when each of the following Falcon A instruction is being executed on the processor. You need to complete the table which is given. All numbers are assumed to be decimal numbers unless otherwise given. If it is a hex number, it would be indicated by H. As a second part of the exercise, we would specify the memory addressing modes for each of the Falcon A instructions given. In the first column, the instructions are listed. We have an example from different functional groups like load, add immediate, jump, store, subtract, shift right, move, and jump on 0. In the second column, you need to place the RTL equivalent of that particular instruction, which you know already by now. On the external address bus, the interaction between memory and CPU takes place, and for each instruction we need to place what data would be available on this address bus. The next column indicates the activity on data bus. We need to indicate what would be available on data bus. The last two columns indicate the memory read and memory write. When read is active, it would be 1, and when it is inactive, it would be 0. And similarly, write could be either a 1 or a 0. Naturally, both of these could not be simultaneously 1, because at one time either memory would be read or some data would be written into. All memory contents we assume are properly aligned. In other words, all memory accesses start at an address which should be divisible by 2. And naturally, if we were considering an example from SRC, then the alignment would mean divisibility by 4, and all addresses need to be divisible by 4. Just as an example, we take an arbitrary value available in the program counter as C348 in hex. The next table shows a partial memory map with assumed value. At a memory address, for example, 20 hex, we assume the contents to be D2 hex, and so on. The data is available in the memory and it has been arbitrarily assumed. For different programs, we will have different data and different addresses. It depends on the program and the assembler. The register map is shown in the next slide. We have 8 registers in this case, and the contents of these registers are assumed arbitrarily again. It could be any other data, but just for the sake of a convenient reference, we have added up some value. I would suggest that you just complete this exercise at home, but just for explaining, I have given you the solution in the next slide. We will explain just a couple of these instructions. Let us say load. The first instruction is load R7, within square brackets R5 plus 12. The RTL equivalent is given as the contents of memory location 12 plus the contents of register 5 are transferred to register R7. So R7 is the destination address. The effective memory address is given by the contents of R5 plus 12, which is a constant given as a part of the instruction. Then we need to tell what is available on the external address and data bus. For this load instruction, the address should be contents of register R5, which from the previous table you could see it is 1, 2, 3, 4 hex. To this we need to add 12. 12 is in decimal, which is equivalent to C in hex. So when we add 1234 plus C, that turns out to be 1240 in hex. So therefore, on the 16 lines indicated by address bus, the data or the number available would be 1240 hex. In the same way, on data bus, as the instruction load is executed, the memory at location 1240 is to be read, and the contents of this location would be brought to data bus. And just look in the previous table, the contents at location 1240 are 785 hex. Now in order to execute and fetch read data from the memory, we must have memory read control signal activated. So MR in the next column is written as 1 and memory write must be 0. Similarly, for the second instruction, add immediate R2 R4 31. RTL equivalent R4 plus 31 placed in the destination register R2. Notice, in this case, only the registers are involved. The external bus is not activated. So it is irrelevant, and we have indicated question marks or unknown. In this case, the read and write signals both are 0. That means these are deactivated, and as a result, it is immaterial what is available on address and data bus. Similarly, the next instruction, jump 52, in the form of RTL equivalent, says PC should be incremented by 52. In this case also, external buses are not activated, both our read and write signal for the memory are 0, and the data on address and data bus is of no consequence. Now you can just go through the next instruction, store, which is just the opposite of load. And in this case, we have the RTL equivalent, meaning that the contents of register 1 are to be stored at a memory location given by R3 plus 17. Now this is important. In this case, the write signal is 1 and read signal is 0. So write is activated. Now where we want to place the data, the effective addresses are 3, which in this case the contents are C2 EF in hex. Decimal 7 after conversion to hexadecimal, when we add, the result would be C300. Now also note that the storage in the memory is big endian. That means the higher address would have the lower byte stored to the memory. So therefore, when we go to the partial memory map, we see at address C300 and we feed 44, or we store 44 at this location, which is already indicated. In the next address C301, we have the lower byte given by 23 hex. So that clearly indicates that the storage is based on writing into the memory, and it would follow the big endian convention which we have assumed, or the designer as a part of ISA has dictated the big endian storage. Now you could go through the other instructions in the same way and define the activity on the address and data bus and the control signals in the form of read and write memory. The next table gives you the solution to part B, where you need to indicate the addressing mode for each instruction. In the case of load instruction, the first one, you could see the addressing mode is a displacement mode. Add immediate has immediate addressing mode. Jump has PC relative addressing mode. Again, store is a displacement mode, and next three instructions, subtract, shift right, and move, only involve registers, and therefore these are register addressing modes. And the last, jump on 0 instruction has a relative addressing mode. As indicated in the previous lecture, the relative addressing mode is always PC relative in the Falcon A. Displacement addressing mode is the same as based or indexed. It is also the same as register relative addressing mode. Today we have a fairly good idea of what control signals are and how these are generated. We'll continue next time with the control signals and explain these with reference to execution of other important instructions. Till next time, Allah Hafiz.